of the whole workshop, okay? And first, I thank invitation from Bao and Andre, okay? In fact, the second thing is some confusion in the program. In the programming totally is, my talk is industrial mathematics. But their program is this title, okay? So I will talk, because of time, I will just talk about the numerical method for the 2D fractional convection-diffusion differential equation, okay? And about industrial mathematics, if someone has interest, we can talk a discussion personally, okay? So this is a journal work of the 3 Chinese guys, but the main work was done by she. She was, by her. She was my PhD student, in fact. And this guy is originally introduced the fractional partial differential equation. She borrowed some idea from his paper, so, and she wants to put his name as co-author, okay? And I didn't do anything, okay? Work only done by her. So I just make advertisement for her. So first I talk is about the motivation, why people recently talk about the fractional differential equation. And then I give some reference about applications and how is the typical books for the issue. Then I will introduce some equation, the space and fractional problem. In fact, recently there are 2 types of fractional differential equation. One is for time, one is for space, okay? And time fractional differential equation is quite easy because it's a one-dimension issue. And generally, people don't pay too much attention. But the spatial fractional differential equation is a little bit complicated, especially for high dimension. Today, I think most simulation just done by the 2 dimension for the finite element method. And very few paper for the high dimension because some, introduced operator made things complicated for the simulation. Then we introduce some numerical scheme. That is, we use discontinuous galactic method for the fractional space derivative, and use the characteristic method for the time derivative. So it's a joint method, okay? Then we give some stability and error analysis result, just a very short theoretical result. Finally, you give some numerical examples. So I will not give the conclusion section, but I will give some advertisement instead of the conclusion, okay? So the fractional derivative in calculus was can be back to 1695. That's the first people to draw the issue, because you can see the derivative for the f. First thing for the f is a power function. It's about x. So if n can be half? That's the question. Afterwards, many people do many things. Many famous mathematicians consider different function, x power n, exponential function, and sine function, cosine function, many, so on. And afterwards, after 10 or 100 years, nobody mentioned it sometimes, because I think because the application issues did not do anything, okay? So recently, the classic book for the fractional calculus is this things. This is a classic book. So most people working on this read this book. So there's recent books, okay? So if someone wants to do some research on this issue, and this is a good book. And recently, so most people pay much attention for fractional differential equation because many applications. So there are many applications. I will not one by one to list. I just give list here. There is some paper. I will give some reference. There is one reference that's very good. And so many applications you can use appear the fractional differential equation, fractional calculus. Okay. So this is an interesting paper. The journal is not a good journal, a very good journal. Okay, but this paper is some survey paper. They give several applications from the modeling and to the fractional calculus So give some details. So if you want really to see some applications, then this is, I think it's a good paper. I read the papers. So, and then many people work on this, how to say, these equations recently. And so most of the application area, and in this area, this is the famous guy. Almost every paper on fractional differential come to his hand to referee or to decide if accept or not accept. Okay, but he's a hard guy. It's not easy to get approval from him, even his students. Okay, so this is more equations, more papers about this issue. Okay. So, what is a fractional derivative? Okay. This is Portuguese. Okay, I didn't change the title. Okay. So, there are many, how to say, fractional definition about the fractional derivative, more than 25. But mostly used is two. One is Riemann-Liouville derivative. Well, this is defined, in fact, by the power function, x power n, you can rewrite about the gamma function. So use this one, you can define the fractional definition, fractional derivative. That means you introduce some weight function here. So then you introduce some operator. So this is an integrated operator. So instead of derivative f, you derivative here. So it's quite easy to do that. So alpha is bigger than or equal to a minus 1, less than a, in this case. So this is a derivative. And this is left. Why left? Because his a is the interval a and b. So you put a here, then it's left. If the b here, t is here, then it's right. So it's left derivative, fractional derivative, and right fraction derivative. There's different. Okay. And I meet some question because many people use that. So derivative is a local property of function, right? And the integral is global. So what is the property of the function about the fractional derivative? So different people have given different explanation. But generally people think it's about global. Okay. So another, how to say, most used fractional derivative is this guy. This guy's still alive, okay? Yeah, I don't know when he died, okay? He's from Italy. He is not a mathematician, in fact, okay? He did his PhD. His undergraduate programming is physics, and the PhD, master is mathematics. PhD is geology. And because his research required some things, so he defined it this way, okay? And then somehow he related to f derivative, okay? And so far, there's some proof. So Riemann-Liouville derivative, fractional derivative is equivalent to this derivative. There is. Yeah. But there are about more than 25 definitions. Nobody discuss other things. My guess is all of them are equivalent. Because if alpha to the integer, the same thing should be, right? Not necessarily. That's a very weird one. Yeah. Because it's a problem of calculus of pseudo-differential operators in general, so itself is not. In fact, this one I don't think is equivalent. No, there's some proof. It's a paper. There's some paper prove that. So if you think some example about the x, y equal x, so then this is a function. If you think alpha between minus 1 and 1, then you can get that y equal 1, alpha equal 1, then is regular derivative. And alpha equal minus 1 is the integral of y equal to x. So this the derivative from here to here when moved to alpha. Okay. This is a fractional derivative. It depends on alpha. So now we discuss our equation. So we consider about this equation. So the time derivative is integer is 1. And then here is fractional derivative. So here alpha is between between 1 and 2 alpha beta. So that is about almost quadratic equation. So it's one equation. And then if you do numerical simulation, you don't know how to do that. So then we give some idea, okay? So what we do, so this question is somehow some people work on this problem. For some numerical for fractional CD problem, first about the finite difference method. So there are several papers. One is this paper, the early paper, 2007. So there's a finite difference spectral approximation for time. So time is quite easy. So this is quite easy. Then is for the, how to say, 3 dimension also is time. So the same thing, in fact, just space time, you increase the dimension. But to treat the fractional derivative is the same as the first paper. Okay. No. Here, just the partial differential, partial derivative in the direction. Yeah. So this is also for times here, not for spatial. Even for spatial, just 1 dimension, okay? So it's for spatial, okay? Also is only one, this is also time, space-time fractional equation, but it's 1 dimension. And then this second order also is 1 dimension. And they consider some, how to say, there's 2 papers discuss about discontinuous analytic method for the fractional differential equation. So this is 2 papers published, 2009 and 2013. So, in fact, theoretical result appeared in this paper for the spatial fractional differential equation. So this is 1 dimension, not a 2 dimension. Okay. So now we want to solve the problem. We introduce some variables. So we introduce P. P is not a operation for the different from Levi-Stokes equation. Here just some auxiliary function. So introduce about the gradient of U, okay? And then I introduce sigma. Sigma is some integral operators instead of the fractional derivative in the original equation. So this was here. And then we can change the equation. This is so regular differential equation. So it's quite easy to treat. And then this is integral equation. So this is trouble. This makes the complexity of the computation simulation. Then this is because it's gradient. So you have, and before you just have 1 equation. Now you have 3 equations. So this is the simulation have more work to do. Okay. So here we introduce some discrete arrangement for space case. So then you discrete the equation. You make how to say inner product. So you can get such equation here. Here also for the integral equation, we also use weak form and make integration. Okay. So then we can get this one. We consider each element use a polynomial approximation, PK. PK is a polynomial with k degree. Okay. So then we introduce that. We get because discontinuous functions have these 2 terms. We have some discrete equation. Okay. Now we didn't treat about time. Okay. Just use discontinuous analytic method for space, fractional space problem. Then we use characteristic method for time. So because you have some estimation about this method. So from this we substitute here, then we can get finely discrete, completely discrete equation. I use that here. Okay. So then we have some symmetricity here. So from here, we finally solve the linear system. Okay. And this linear system is not sparse structured as finite method because integrate equation. Okay. So most case, the system is about the topless structure. It's a block topless structure. So now we start about how to say the stability. So introduce some same norm for the stability analysis. By this one, we can prove that this scheme is well defined. There is a unique solution. And also, we can, with this condition, Frank says this condition is a very strong condition. Okay. With this condition, we can prove that some estimate for here, this is for time, then we can get numerical stability, this one. We can prove that. If without introduce such variables, it's very difficult to get stability. So then we can get the error. The same thing, we can get the error estimate here. So this here, delta t square, and then depends k. K is polynomial degree in each element, 2k plus 1. So this is our error estimate. So now, and I will give some example. So we chose exact solution as this one with initial condition, and we consider B is homogeneous, just 0, to see what's happened. Okay. And we consider t equals 0.1 and make different alpha beta to see the order of error. Okay. And the result, in fact, to the very good, also is better than theoretical analysis. So numerical order of error is better than theoretical order of error. And because we guess, I'm not sure, we guess because the solution is symmetric. Okay. So we did many simulations about that one. Okay. Then, or we consider time equal 1 because the time bigger, a bigger error. The time bigger, error is bigger because they accumulated the error from time. So the error still is very good. Okay. The second example, we consider B is not homogeneous. Of course, the solution is still symmetric. Okay. But the only difference is here. Here is not 0. So, pardon?
Is B a vection in your equation?
B is the equation here. Oh, no, don't worry. It's here, yeah. I don't know how to jump to there. Here, this is the exact solution, okay? This for h equal 1 over 4. The time is 0.05, so that is not very good, but you get some reasonable simulation, approximation, okay? Then we get h equal 1 over 8, h equal 1 over 16. So then it's better than 1 over 4, okay? And t equals 0.1 is bigger, t is bigger. The same thing, h equal 1 over 4, okay? The alpha beta is 1.9, 1.6. In generally, alpha is a little bit approximate 2 in most application. Not exact 2. It's about 1.7 to 1.995 in many applications. So then is 1 over 8, 1 over 16. So this is much better for the approximation. So this is exact solution for t equal 1 and k equal 1 over 8 and h equal 1 over 16. Okay. Then alpha equal 1.2, beta equal 1.5. Here we put t equal 5, the same thing. And alpha is bigger, 1.9, beta equal 1.6. So this one is quite good for approximation. So this is my talk, and the main result was published in Journal of Scientific Computing. And so this is main content of my talk. So there is advertisement. Okay. So next year we have some conference, satellite conference in Foz do Iguaçu, the waterfall city. Okay. In fact, 4 conferences. One is Brazilian workshop on continuum optimization. This is for Martini's 17th birthday. Okay. And also for me, because he said if he alone, he will not do anything. He needs someone to join with him. So then I make, some sacrifice. And because I'm first 61, not 60 anymore, okay, at time. Maybe. Okay. Then the 4th Brazil-China Symposium on Applied and Computer Mathematics, and some national conference in industrial mathematics. And also 2nd BRICS mathematics conference. So this is 4 conferences, the same period, and we chose some hotel called Golden Park International. It was 5-star hotel. Today is 4-star. Okay. But the price is very good. And the first BRICS mathematics conference is in China this year, and about 21 to 25 August in Beijing. And low registration fee, all local expenses paid by Chinese. So China have a lot of money. They will pay everyone local expenses. And because they still want, in fact, at the beginning, they want to pay air ticket too. And I refused, because if they pay air ticket, I have to pay air ticket too. Then I have no money to pay air ticket next year, right? So I refused to pay air ticket. Okay. Pardon? It's my fault. No, it's not my fault, because you cannot give me money. If you give me money next year, then I could do, okay? And so welcome to Beijing if anyone likes to go, okay? And also, because today China has a lot of research funding, and they asked me to ask CMPKO open the joint editor for the research project. They said even CMPKO doesn't support any sense that China can support all necessary research funding. So thank you. For together, the same hotel. Parallel, yeah, parallel. Parallel. Because we got 4 rooms, 4 conference rooms at the same time. Okay. The rent is only 3,500 per day.
The birthdays are in which conference?
This is this one for this one, this one for this one, and this one for this one.
Okay. But this is all at the same time.
Same time. But if you go, you want both, and I change the program such that you stay one, and another time another one.
So you get credit for your registration.
Is it like Disney World? You buy one pass.
But I have to charge a registration fee, okay? Not in China, because we are in Brazil. And but there's something I got, because we can, for the conference dealer, we make a hotel, we can buy wine from Argentina to the restaurant, okay? And you just pay, each bottle, you just pay 20 reals for the opening of the bottle, okay? It's quite cheap. I prefer Argentina wine, not Argentina. And also, perhaps for the Catalata, for the waterfalls, and we can get a discount for the interest.
On which side?
Pardon?
On which side? The Brazilian side?
Argentina, Brazil.
Brazilian side.
Brazil side.
Brazilian side. Because I just have You find someone has power to decide the price for Brazilian side.
Okay.
So thank you for everyone.
Okay, let's thank Professor Yuan.